Good afternoon, everyone. I hope you're all enjoying reInvent so far. This talk is DNS Demystified, where we'll be talking about Route 53, Amazon's DNS service. My name's Gavin McCullough. I'm a system development engineer in the Route 53 team. I've been in Amazon for about 6 years, working on load balancers, DNS, traffic management in general. With us is Juan Shi, who is a software development engineer with MuleSoft, one of our customers, and he'll be explaining their use case for Route 53 later on in the talk. In case you're wondering, a system development engineer is, in Amazon at least, a system engineer who occasionally does some development when the software developers aren't looking. So if you saw DNS Demystified last year at reInvent, it was a 200-level talk. This is a 300-level talk. We're kind of stepping up the level a little bit. So quickly, what we'll be going through, there's a sort of a theme of looking at more large-scale DNS or more production-sensitive DNS. So the kinds of things you're doing where making mistakes in this DNS is a bad idea, or you want to do it at very large scale very quickly. So we'll have a very quick intro to DNS and the core features of Route 53. Then we'll look at some DNS inside EC2. We're going to look at some of Route 53's new features. We'll have a case study from MuleSoft. And then we'll look at some of Route 53's advanced traffic management features. And finally, there's a few little tips on DNS operational excellence toward the end. So let's start with the rapid intro, get that over with quickly. I'm guessing most people here are reasonably familiar with DNS. Hands up if you're familiar with DNS. Feel like you are? OK, we can go fairly quickly. So I'm sure you all know what this picture means. It turns out that in order to connect to a service online, you probably know the name, you probably don't know the IP address, and we need some way to find out what the IP address is. The way we solve it is there's a DNS resolver. It's in just about every network. There's thousands of them across the internet. And as a service owner, when you're building a web service, you need to make sure that all of those DNS resolvers can answer the question. So what you need to know is, how do the resolvers answer the question? Well, it turns out they talk to the authoritative servers. And the authoritative servers are arranged in a kind of a tree. So initially, the roots own everything. Every name, in principle, is owned by the roots. And what the roots do is to say, well, this is too much traffic. Set up some separate name servers for com. I'll delegate to them. Some more name servers for an org, and we'll delegate to them. And they, in turn, delegate further down. So the tree is distributed, and management of it is distributed. Not everybody wants to run their own DNS servers. So this is one of the reasons the Route 53 exists. So what a DNS resolver actually fundamentally has to do is to know where the root servers are. That's the one piece of information it must have. And so it will start at the top, query the roots, and basically all of the information that's needed from there can be got by querying down through the tree. You're probably all familiar with this tool. It's called dig, and it will give you a trace which shows you exactly how the resolution path goes. The first step is we know what the root name servers are, and we choose one, which on this occasion is mroot. And we query it for www.reinvent2017.com. And we get back, no, I don't have that. Talk to one of the com name servers. And we choose L arbitrarily. When you ask the L root server for www.reinvent2017.com, regretting that name already, what you'll get back is a further set of delegations to say, oh, that zone's on these Route 53 servers. And so you query those Route 53 servers, and you get back an answer. And one thing that's interesting to point out here is you also get back the NS records. This happens at every delegation. You get the NS set from both the party that's delegating and from the party that's delegated to. I won't go into that more here, but it's important later on in the talk. It's a useful property. So you want to set up a web service. We have to create our zone, the pink one there, and we have to attach it to the tree. So what does Route 53 provide in this space? Well, we have zone hosting. In particular, we have 76 POPs, which are little small data centers around the world. And so we're close to all of your customers pretty much. We provide a 100% availability SLA, which is relatively unusual. But DNS is that kind of sensitive service that outages are really not acceptable. And so what the public DNS service does is allow you to establish your zone and have it hosted online without you doing anything much. So then you want to attach to the tree, and the Route 53 registrar is there for that. Registrars allow you to book a name and set up a delegation in whatever the TLD zone is, COM in this case. We also have private DNS as a service. So if you've ever managed an on-premises network, you probably wanted to set up a whole load of internal-only DNS names. That's a common enough practice, and it's common also in EC2 VPCs. So what private DNS allows you is basically the ability to do that. We also have a health checking service and traffic management, which I'll go into a bit more later. And we have one of the things, thinking about DNS on a large scale, that you should really be aware of is that everything we do has APIs. Everything we do also has command line tools that call the APIs. So it's really straightforward to automate all of these processes. If you are doing DNS on a large scale and you're still doing it manually, it's fine, but A, it'll be slow, and more to the point, actually, you've still got a lot of human error there. It's very easy to make mistakes, and DNS outages can be pretty severe. So it's better to automate, and all of these tools, everything we show, will have relatively straightforward automation paths. So very quickly, we want to register a domain, so we can call the check domain availability API call, and we get back an available for this domain. So we register a domain, and then you can list operations there, and we see that it's in progress. It takes about an hour to register a domain. The zone was created automatically. If you didn't use Route 53's registrar, you don't have to. You can just pre-create the zone and use a different registrar. One thing to note is that every zone has a zone ID, which is very important within the API. You can have multiple copies of the same zone, so we need an ID to be able to distinguish between them. So we create some records quickly, change resource record sets, and you're passing it a JSON document there and saying in that zone ID. Now, an important thing to note here is that there's a status of pending on this. So what that says is the API has accepted your change, we validated it's a sensible change, and now we're propagating it. So it isn't ready for your use yet. And we've given a change ID. And what that allows you to do is to come back and query Polis and say, OK, what is the status of that change? Usually within 30 seconds to a minute, it will change to in sync. And what that tells you is that all 76 POPs are now in sync with your change. And no matter where you query in the world, you'll get the right answer. What did the JSON document look like? It's an action of create and basically a simple description of the record that we created. So I mentioned DNS inside EC2. You don't necessarily always want to put all your DNS records in public DNS. If they're private records, why would you want to tell everyone on the internet, including every nefarious individual, what your DNS structure is? So inside EC2, if you need DNS records to allow your services to connect to each other, that's no problem. When you set up a VPC, by default, we automatically enable a DNS resolver for you. And the DNS resolver includes host names automatically for all of your instances. If you want, as I say, to create arbitrary other Route 53 private DNS entries, you can do so. So basically, you call the same API, you say, create a zone for me, please. Oh, and associate it with this VPC. And so you can create records, you can change them, all of the same in-sync and pending statuses apply. So how does private DNS actually work? The EC2 DNS resolver classifies queries, and it gets a little bit of extra data. So when you send a query from your VPC, the EC2 DNS resolver will receive the query along with some extra metadata, such as what VPC are you in, and what features have you got enabled. And it is able to reason on that basis that this name that you've queried is something that is within a private zone in this VPC. So instead of forwarding the query to the routes and going out and doing full recursion, it will just send them to the private DNS authorities. So as a result, none of these records are ever visible to anyone except in your VPC. So a common enough problem for people moving to the cloud is to be able, we've already built a large infrastructure on premises. And you want to move into VPCs, but you can't do that overnight. So typically what people do is to set up a VPC and direct connect your on-premises network to the VPC. And what that allows you to do is you've now got IP connectivity between instances and your hosts on-premise. And you may have a substantial number of services on both sides. So what you now need to be able to do is to do DNS resolution across. So the problem there is that, well, initially you just say, OK, well, I'll just forward queries between the two. The only difficulty with that is that the EC2 DNS resolver is not a real instance inside a VPC, and it isn't routable across Direct Connect or VPNs. As it stands today, we have the most standard solution to this problem is to set up a couple of instances inside the VPC to do forwarding. So they can obviously connect to EC2 DNS directly, and you use them as kind of a bridge. We recently wrote a white paper on this topic, so if you are using a hybrid cloud and you're trying to solve EC2 DNS or an integrated DNS between the two, it's worth having a read of the paper. So this is kind of the picture I'm talking about. You have on-premises clients using probably Active Directory or Bind or something on premises, and then you have your EC2 instances using EC2 DNS. But what we've done instead here is we've set up this highlighted forwarding resolver. And so the EC2 instances now talk to it directly, and it has rules to say, these types of names all go to Amazon-provided DNS, the EC2 DNS, and all other names or some other names go to the on-premises. And so you can just set up rules to solve that. Equally, the on-premises clients, or the on-premises DNS resolver has similar forwarding rules that you just set all of your EC2 names, send them over to the forwarding DNS resolver. And at that point, you pretty much have a single view of DNS. One of the things that's brought up in the white paper that's worth noting is there is a limit on the number of queries that a single instance can send to EC2 DNS. And that is about 1,000 per second, which for a small VPC is not really an issue. But it is something to think about if your VPC is getting large or if for some reason you make a really large number of DNS queries. So what are the new features in Route 53 in 2017? One that I'll talk about in a bit more depth later is Geoproximity. So this is a routing type to choose between different endpoints. If you're a public Route 53 user, we've launched query logging recently. So if you want to know who is querying your zone all around the world, you can get your query logs back. This is usually useful, for example, in security processes. Maybe you want to know that people are doing large numbers of queries against your zone, trying to find out what names are in there. Or maybe you are very careful when you go to delete records to not create outages. The nice thing to do is to say, well, has anyone queried this record in the last week? So a further one is we use weighted round robin, or we offer weighted round robin DNS, which is essentially like a poor man's load balancer. And up to now, you have had to always return a single record at a time. But now we have launched multi-record answers, so you might have 10 or you might have 100 entries in weighted round robin. And it may not suit you to only return one answer. You can return 10 answers, and the benefit of that is that the DNS resolver that caches it will rotate through them in most cases. And you can potentially, in some situations, get a better load balance. Another new feature we have is the CAA record support. So CAA record support is, the CAA record at least, is for certificate authorities. You can essentially create a record that says, no certificate authorities should create certificates for my domain except these ones. And you're basically preventing someone else from impersonating you there. Finally, there's a service limits API. So if you've used Route 53 or perhaps any AWS API, there's always some kind of limits to say you can only have this many zones by default or this many records in your zones. And this allows you to automatically query this and find out how much of your limits you're using. Finally, there's a beta feature we're going to talk about here, so you can all feel very glad you came. So this is something that we've not actually fully released yet, but we're interested to get your feedback on it. So as it stands, I mentioned before that the DNS service itself has a 100% SLA. So we say that we will always answer your customers' queries. And we use, in order to do that, we have this really distributed POP network around the world. However, we have the change mechanism, an API, and the propagation mechanism are more centralized. So they're built in US East 1. And occasionally, you can have an issue where there's an issue with that, and we will perhaps delay propagation. It doesn't affect the records actually resolving, but the propagation's a bit slower. For most customers, that's not really that big of a deal, but there are actually a few customers for whom that's a big deal. So I'll give you an example of ELB. When you ask for an ELB, one part of their workflow is they have to create a DNS record for it. And they need to know that it's propagated before they will give it back to you. So if we have a delay in propagation, ELB has a delay in creating ELBs, and that's unacceptable to them. So for them and for other customers who have that kind of synchronous workflow, we've created a second API, which is basically a second, largely independent propagation path. There are some trade-offs in this that I'll go into in a minute, and we'll also show, MuleSoft will explain how they've used it. So this is the current setup. You have an API client, it calls our US East 1 API, it's one API for the world, and that propagates, so initially, that will return your change as pending. We'll propagate it out to the world, and then the API will switch to start saying that it's in sync. And what we're adding here is a second API. And so now, if you'll notice that there are no lines that go between the US East 1 API and the EU West 1 API. And the reason for that is that we want to keep them very, very separate. The whole point of this exercise is to make sure that there are almost no events that could impact on both. So if we start shuffling data back and forward between them, the possibility for some contagion starts to arise. So as a customer using this model, you essentially have two unsynchronized copies of your zone. Now, what you actually do in practice, or what we recommend you do, is you write all your changes to both sides. And so you're essentially maintaining two copies of the zone. When you make a change, you include a version number on it. And we propagate both of those data sets down onto the POPs. And so the POPs look at both sets and coalesce them into one view. And where there is a distinction between the US East 1 API's answer and the EU West 1 API answer, we choose the highest version number. So you're in control over which one will win. So I'll invite Joan now to come up and explain their use case of Red 53.
Thank you, Galvin. I'm Xuan Shi. I'm a senior software engineer from MuleSoft. I'm going to talk about how MuleSoft utilizes the multi-region Route 53 services, which is a propagation sensitivity use case. I'm going to give you a brief introduction on the architecture of our cloud platform first, then show you how we use Route 53 service, and then finally, how the multi-region Route 53 service improves the resiliency of our cloud platform. So first, a little overview on our company. So we have been helping companies to build and scale an application network of apps, data, and devices through APIs and integration. We have been supporting customers in over 60 countries. So what do we offer to our customer? So we offer a multi-tenant integration platform for APIs and integration, which provides high scalability and availability. So our goal is our customer can focus on their needs in their solutions in integration, and we take care of their infrastructure problem. So we offer both on-premise and the public cloud solutions. So today I'm going to focus on the public cloud solutions, so which is built on top of a lot of AWS services. We provision instances in EC2 for our custom applications. We're using SQS for messaging, S3 for data storage, and so on. Just give you a rough idea on the scale of our platform. We host around 25,000, we actually more than 25,000 custom applications in AWS cloud and over 12 regions. And we do around 9,000 EC2 instance provision and termination daily. And for each instance, we also do a Route 53 DNS records update, and we try to create a DNS record for each instance of our Mule applications. So let's take a look at the architecture of our platform. So those are the Mule applications running in the cloud, which is AWS cloud, doing integrations for our customer. Our Anypoint platform provides a management center, which is a portal for our customer to deploy applications into the cloud. And we also have a we have a lot of load balancers, which is the entry point for those Mule applications. So customer can hit their applications through our load balancer or directly to the workers, to those Mule applications. So where are the DNS operations in this architecture? So the Anypoint Platform Management Center is responsible for creating all the DNS records for all those Mule applications. And our load balancer and our customers are the consumer of those DNS records. Just for example, our customer can use the management center to create a Mule application named app. It automatically gets a app.cloudhub.io domain, which is routed to our load balancer. And our load balancer proxies the request to the actual Mule application, which runs on an EC2 instance. It has another domain, is mule-worker-app.cloudhub.io. So how do we apply those DNS configuration? We have a deployment transaction. Here is a simplified flow chart of our deployment transaction. We first provision an instance in EC2. We set up a lot of meta info, set up health monitoring. We then launch the Mule application onto the EC2 instance. We run the Mule application, and we make sure the app is up and running. Then we apply the network configurations, like apply the static IP onto the instance, or apply the DNS configuration on the instance. And finally, we verify it's working. Then we hand the application back to our customer for either testing or production working. So what exactly do we do with the DNS configuration step? So we have a DNS record. We want to make sure it's somewhere. The domain name is mule-worker-app.cloud.io. It is mapped to some IP address. We make a change resource record request to Route 53 API. Then, as Gavin has mentioned, the Route 53 API would then propagate the DNS record to all its edge locations, then which made them available to the rest of the world. As you can see, the Route 53 is very important to our platform. So without the Route 53 API services, it will be a challenge for us to apply all the DNS configurations for all our applications promptly. So let's see, as Gavin had mentioned, let's see what can go wrong in this graph. Just basically, even if it's a short period of unavailability of the service, it can be a huge impact on our service to our customer. So there are generally two kinds of failure mode. First is the API could be unreachable, or the DNS records propagation could be delayed. So the impact on us is our application cannot be deployed properly. So we have to tell our customer to do it again. Or the Mule application is not resolvable, so our customer cannot use their applications in the cloud. So which we don't want that to happen. So instead of a single point of failure in this graph, the Route 53 server in US East, the Route 53 team is providing another API server in Ireland, which also takes requests and do the propagation and has some logic to figure out which DNS record to serve. This is a service they have been using, and we are the first external customer to try this out due to our sensitivity on the propagation. So, as Gavin has mentioned, all the features of this, all the trade-offs on the multi-region Route 53 services. So there are two options for us. First is failover, which is not really recommended because that will result to two different sets of DNS records in two servers, and it's hard to maintain in a long run, although it's simple to implement. But we didn't choose that road. We chose to use it redundantly. As Gavin has mentioned, we apply the identical request. We send the identical request to both servers and try our best to make sure both servers has the identical set of DNS records. So here is the implementation of our use of the multi-region Route 53 service. So there are two Route 53 API servers, one in US East and one in EU West. During the deployment, during one of the steps in the app deployment, we send the request to both servers and to insert a new DNS record for our Mule application or delete an old record of Mule application which is being shut down. If both requests are failed for some reason, which has never happened so far, we will have no option but to fail our application deployment and to tell customer to do it again. If one of the requests is successful, we can continue our app deployment and verify network configuration and hand the application back to our customer. Then the customer can start using their app. And if there is one request failed, we notify our internal synchronizer, which will retry to reapply the DNS record to one of the server in a later time, asynchronously. If there is a deletion fail, so we have a sweeper. We will try to go through all the records in both servers and try to remove any garbage records. This has been working great so far. With this, we are able to avoid a single point of failure. It is much less likely to have trouble to talk with Route 53 service. So far, we have never encountered any problem to apply those DNS records to our Mule applications. There is something to think about as on the rollback plan. So the new multi-region Route 53 service is living on a newer version of API, which is backwards compatible but not forwards compatible, meaning we need to prepare a complicated rollback plan in case something goes wrong. We want to switch back to the single region Route 53 service. There is still a small chance that the DNS update could be delayed if both Route 53 servers are having some issues in reachability and the propagation, respectively and alternatively. But it is recoverable by our implementation. So as a conclusion, I would say the multi-region service has been really helpful. We are able to avoid any potential disaster and provide even better services to our customer. With that, I'll hand back stage to Gavin.
Thank you, Xuan. It's really interesting to get your point of view on it, having used this in production. Just as a recap on this, so we've added a second API to give you a second propagation path and to remove, as Xuan says, a single point of failure. Best practice is very much to use both APIs. Route 53 is quite particular about its availability, and one of the things that we've learned in architecting services over the years is to try to always maintain constant work. So if you can envision a situation where this event might happen or that event might happen, what you want to be doing is doing the full work all the time. So that what you don't want is an occasional event where suddenly you say, oh, I'll switch to this endpoint and ramp the workload up. Because that's going to hit you with a surprise at some point. When it finally happens, you'll hit a throttling limit or find some bottleneck you've never discovered before. So the idea here is to always be doing the full level of work on both APIs. I say it's not currently released yet, it's private beta. This is not to say that we're not confident in it. I mean, ELB and RDS are both using it, so we're very confident with it. I guess the beta status is we're not 100% sure that it's quite polished enough in terms of API and interfaces for customers to use. We have no console support, for example. That being said, if you have the kind of use case where this kind of synchronous you'd be waiting on this propagation is important, you're absolutely welcome to talk to us. We'll be here after this talk, or in general, we would love to hear from you, and if you would like to use it, we'd totally set up a meeting and discuss your use case. So let's talk a little bit about Route 53's traffic management. So DNS itself, as I'm sure you're aware, is an abstraction layer. We're doing translation of names into typically IPs, sometimes mail servers, other things. And so there's an opportunity here to do something smarter than just giving static answers back. So we'll look at some specific customer use cases that we've solved doing this and that are available to you. So many years ago, an online bookshop you may have heard of, they used to run things on multiple data centers. And the first question was, well, how do I balance load between these data centers? I have load balancers in each data center, but I need something outside to actually direct the traffic to each one. So DNS was used for that, and we used weighted round robin. And essentially what that is we have all the DNS resolvers talking to DNS, and we direct them to one of the 3 or 10 or 200 endpoints. And we can associate weights with each one so that our authoritative DNS will hand out maybe 30% of one answer and 40% of another. Related to that, and again, something that Amazon was looking for, was the ability to, let's suppose something terrible happens in one of these data centers. Do you want to spend half an hour waiting for an operator to join a conference call and make some changes in DNS? No, ideally not, please. So we have an automated health checking facility, and what that will do is poll all of the endpoints. And maybe it'll make a get against slash or against slash status or something like that. And the answer typically must be somewhere between, the status code must be between 200 and 400. And if it's outside of that, if you return a 500 or a 400, we'll mark that as unhealthy and take it out of service. So essentially that's what's happened here. You see the top endpoint has something terrible happening in it apparently, and it has temporarily got a weight of 0. And once it recovers, we'll bring it back into service again. But in the event that this happens, where you have multiple endpoints, one of them fails, you can recover within, if you have the TTL set reasonably low on this, you can recover within 2 minutes. So a kind of related setup, we have a failover routing type. In ideal circumstances, you do want to run on a large scale with like multiple active endpoints all the time, so that you're not kind of running a cold standby, but that isn't always possible. So, for example, in some situations where you just have a master and a cold standby, we can deal with that. This is the kind of setup. A typical setup, maybe the secondary is a full-fledged service that can run, or maybe it's like a read-only copy, so it will take over. The customers will get a degraded but still useful service in the meantime. Or maybe even just the second one is like an S3 bucket website with a gone fishing page that says, we'll be back shortly, but it's better than a failure. So something's happened to the primary now. All traffic will shift off the primary, or all DNS answers will shift off the primary to the standby, and typically customers will follow with it. So very important in building web services, I'm sure you all know, is latency. And a common setup these days with so many cloud regions, particularly in AWS, is how about I build my service in 10 different regions, and then that will handle the latency, right? And the question is, well, how do you actually get your customers to go to the right region? So what AWS is doing is keeping track of, we instrument a lot of Amazon's big web properties, and so we actually have data on all of the IPs in the world and what their latency is to the different AWS regions. And this allows us to, on the data plane, as the query comes in, look at the IP address that it's coming from and say, that region is the quickest, give them back that region. So the picture is something like this. You may say, well, we have some people in the Far East near Tokyo, we have a lot of people in the US, we have some people in South America, and some people in Australia, so we'll build it like this. And you set it up, you basically say, here's where my endpoints are, please just do it, and we will look after the rest. So what if your endpoints are not actually in EC2? Maybe you have your own data centers. Now that database is very much aimed at EC2 regions, so we don't really have data on every pair of IP addresses in the world. So you may want to have a look at Geoproximity instead. This is the recently released one. Another thing that's kind of useful is to be able to get a little bit more flexibility in how the traffic is moved around. And this also provides that. So the typical case, what we're actually doing here is we have locations, map locations for the IP addresses, and also for your services. So you picture a situation where you've got an endpoint on the East Coast and an endpoint on the West Coast. And if you set up Geoproximity, by default, what will happen is the customers will be given the answer that's closest in distance to them. That isn't necessarily the closest in latency, but it's not a terrible proxy for it. And so what you see here is everyone west of that line will go to the West Coast endpoint, and everyone east of that line will go to the East Coast endpoint. And one of the things that you'll notice looking at that picture is that the East Coast endpoint is loaded more than the West Coast endpoint. And that may or may not be a problem, but if it is a problem, you can address that here. So I set a bias on the West Coast endpoint. And what that's essentially doing is skewing the distance calculation somewhat, and essentially attracting more traffic to the West Coast. And now we've evened out our traffic load. So Geoproximity gives you a bit more flexibility to maybe bend the pure latency rules to solve load problems. Another very common requirement in DNS is to be able to say, okay, well, I have different endpoints with different languages or different endpoints with different content depending on where the customer is. So geolocation offers you the ability to say, based on the continent the customer is on, or the country, or within the US, even the state, which endpoint they will get back. So a typical picture is something like this. You have a policy for the North America, a policy for South America, a policy for Europe, and then a blanket policy that covers everyone else. So I've talked a lot about these kind of specific policies, and it's very common to use a number of them together. So you would frequently say, okay, well, I've got, I want my website running, I want it low latency, so I'll use LBR. I want to maintain health, so I'll use health checks. And it's multiple endpoints, so I'll use weighted round robin as well. And it can become a little bit difficult in terms of a flat zone file layout to actually reason about what's going on. Things can get a little bit complicated. The other thing is that when you have a complex policy like that, you may need to make multiple changes in one step, and you don't want to go through some weird transition mode. So you want to be able to make atomic changes with 2 or 3 or 4 changes at once. And finally, if you're an operator on a fairly big DNS service, you should always have a rollback plan. Just on the off chance it doesn't do exactly what you thought, you want to be able to roll back rapidly. So for all of these, with all of this feedback, we built Route 53's traffic flow UI and API. So this is an example of the Route 53 traffic flow UI. And so what you can see here is kind of like a logical picture of a weighted round robin rule. In this case, the 2 endpoints, one of them is an ELB, one of them is just an A record. They don't have to be the same. And to just show the kind of level of complexity, we also have health checking set on those. And if you want to see just the level of complexity, I mean, I was at it for a little while, and I thought, okay, well, I'll have a geolocation, and then I'll have a failover rule just in case this goes badly, and I'll have a weighted round robin, and things start to grow. And this is a much easier way to envision what's actually going on and to edit. Again, as an operator, it is very useful to be able to get your colleague to code review something. So traffic flow policies are all standard JSON text documents, relatively readable. I don't want to spend too long reading this, but basically there's a section with endpoints and a section with rules. So you can pass it to a colleague to have them code review it. Once you go to create that policy, one of the things about these traffic flow policies is that they're immutable. So if you create one, you cannot overwrite it. So what happens here is we've recreated one or attempted to, and what's happened is we've got a version 2. And that means that the version 1 is still there for us. So now let's apply version 2. It's a simple command. And if anything should go wrong, if we're not satisfied with how this is working after a few minutes, just roll it back to version 1. It's very simple. OK, so last section, a few DNS operational tips. It sounds like everyone in here is a DNS ninja, so apologies if this is lost on you. But working in Amazon for a few years, we've become very sensitive to DNS. We've had lots of little tips that we have that we kind of bring the new guys onto. We thought we would explore 1 or 2 of them here. So TTLs are really, really important to think about. It's very easy to just take the default. But as a general rule, you should be thinking about TTLs. This is one of the unsung, really useful features in DNS. So what a TTL is, just very quickly, is all of those resolvers that are constantly accessing your DNS. Every time they get an answer, they get back and don't come back to me for this long. You can just keep using that for the next 60 seconds, hour, 2 days. And so it's important to think about that. How quickly do you want the world to change or to pick it up when you make a change? So if you have something like a health check record, or maybe weighted round robin where you want people constantly coming back in case you're changing the weights or whatever, you want to have a short TTL on that, because that will give you the responsiveness to be able to get a bad endpoint out of service quickly. However, as a general default, unless you can envision a situation where you want to change that record quickly, you probably want quite a long TTL. There's no great cost to it. It gives a better customer experience. When actual customers are connecting to your service, they will no longer see the latency of a DNS lookup. They'll just talk to their local caching resolver, and it will just give them the answer straight away. It also lowers your query volume, which lowers your bill, which is kind of nice. One exception to that, for critical changes at the time you're making the change, you want low TTLs. So let's suppose you have a record that has a 2-hour TTL. You make a change to it. Now, you want to roll back. A whole load of resolvers around the world have now cached that, and they'll come back to you in 2 hours to get the new version. So your rollback is going to take forever. So typically what we would do as a matter of best practice is lower the TTL first, give that some time, and then make your change. And make it with a low TTL in order that if you don't like the result, you can very quickly roll that back, and all of the resolvers will spot the change and move back. And then at the end, you raise your TTL back up again. So a sort of a particular example of this isn't switching DNS providers. I'm not, this applies to every vendor, not just Route 53, but I'll use moving to Route 53 just as an example. So the simplest solution to move a zone onto Route 53 is you export the zone data, you import it into a new zone in Route 53, and you just change the registrar settings, and traffic will gradually shift. But the problem is that the TTL on a lot of these records is 2 days. So if maybe you've got a geo record on the old and a geo record on the new, and they don't quite line up the way you thought, or maybe you've made a mistake, maybe the import didn't exactly work the way you thought it was, or there's some reason that this isn't working how you thought, you've now got a 2-day rollback time. So there's a way around this. I mentioned before that there are 2 copies of the NS records. It turns out that DNS resolvers, it's not that well specified in the RFCs exactly which one of these NS record sets matters most, or which should be cached by DNS resolvers. So there's a picture of it here that I showed before. The TLD gave us a set of NS records for this zone, and then the in-zone resolver, the in-zone name server gave us a set of NS records as well. And so the resolvers essentially get to make a choice between the two. It turns out that bind and unbound and a couple of the other popular ones tend to use the in-zone, the authoritative name server records, but there are some significant name servers that use the other set. Now, you don't get to control the TTLs on the top set. You only get to control the ones on the bottom. The ones in the com zone are 2 days, that's it. So here's our starting point. We've got 2 zones in production, or rather 2 sets of NS records in production, one in the com zone and one on our existing provider. Now, we've created a new zone for reinvent2017.com on Route 53, and it has its NS records. So the first thing you do is you lower the TTLs on the old provider and on Route 53, because both of those are going to be in service shortly. The next thing we do is we change the old provider's reinvent2017.com zone to point at Route 53. So you can picture a bind resolver now. It's worked its way down through the route. It's queried com. It got back that long set of TTLs, and that pointed at the old provider. And then it makes another query against the provider zone. And what it gets back is the answer, but it also gets back these NS records for Route 53. And it will go, OK, I prefer those. Stick them in the cache. So now, for the next 10 minutes, all of its queries for this domain will now go to Route 53. This is kind of called a sideways delegation occasionally. So now you can, having made that change, you sit and let it bake. You watch your monitoring, you watch your dashboards, you see if there's any drop in traffic, you ask your support team if you had any calls, and now when you're confident, you raise your TTLs back up. And this is kind of solidifying that change, but you've had some time with the low TTL with a rollback plan. And now, finally, you now go to the registrar and make the change. And so the benefit here is this was the change you were going to have to make all along, but you've been able to do so with a couple of steps to kind of bake it first with a quick rollback. Finally, you're about to turn off that other DNS provider. There's a whole bunch of situations where you'll be surprised that there's still traffic going to that. There's a resolver that doesn't do what you think it does. There's glue records sitting around somewhere that might surprise you. And generally speaking, what you want to do, if you have to blind turn it off, do it with a rollback. Like, think about, just in case this goes wrong, how do I turn it back on again? If you have query logs on that provider, go look at the query logs. See who's still querying it, or what percentage at least, if maybe there's a metric for it. But yeah, have a rollback plan, and do your monitoring when you're turning that off as well. Really, really important. OK, so quick summary. We've looked at Route 53, which is our low-cost, high-availability DNS service. We've looked at all the flexible traffic management features we have and some of EC2 DNS. It's important to note that all of this stuff is fully automatable. We have APIs for everything. You can code everything. There are command line tools for everything. A lot of them are third-party command line tools as well. And the thing to keep in mind is it's both more efficient and it's much safer to do things that way. Finally, we had a case study from MuleSoft. Thank you very much, Joanne. And we had some quick operational tips, which hopefully some of you will find useful. OK. Many thanks for listening. We'll be around after the talk if anyone would like to ask us questions about anything at all to do with Route 53. We're totally here.